Hopefully it's not been too hard. And yeah, halfway through, just keep trucking along and just survive. All right. So today's lecture is it's material selections. You had an asynchronous lecture about this. We go into a little more detail here, and then we apply what we're going to learn today to something that'll help you forego or forestart the one section of your project with your bioreactor. All right. So uh, project specific material selection. What we're going to talk about today is what material selection is and how that is different from concept generations. Then we're going to introduce the main tool for material selection, which is Ashby Plots, how we use Ashby Plots either visually or by quantitative analysis. And then we're going to do some examples because the best way of showing how to use something is through examples. And then we talk about other Ashby Plots before we get into the project specific analysis. So, and of course, feel free to comment in the chat. I'll answer questions at the end of this lecture if you do have any questions in the middle. So, what is material selection? How is it different from concept generation? So, concept generation, when you generate a concept or generate an idea for a system, right? Many materials appear attractive, appear like they're going to be appropriate for your system. You have many unique concepts, and you might have a threshold of materials you would like to utilize for them, right? Um, but unfortunately, generating an idea of concept with materials is different from material selection because when you get into the nitty gritty of deciding how you're going to work on the specific aspects of your projects, particularly what kind of material you're going to use here and here, it's not an infinitely variable. It's not an infinitely variable category you can choose from, right? Uh, Material properties, some material properties are better than others. Some materials are better than doing things than they are at others. And another thing you need to know is that material properties are coupled, which basically means that one for the same material, one property can either enhance uh, or retract the efficiency of another property. We'll get into examples of that later. So you can't arbitrarily choose a material based on one property because it could affect another, which could affect your overall performance of design. Real systems are dependent on the materials that you choose. So what that essentially means is your system, your function is only as good as what you put into it, what kind of materials you throw, or what kind of substance you throw to keep it alive. Right? And if you don't choose the proper one, it's not going to survive for a long time, or it's not going to work in general. So there are discrete materials that best match your application, and it differs from application to application. We'll go over a method of how you can analyze specific how a material fits with your specific problem. But yeah, you need to choose one that's best suited for your problem. And there should be a material that could do that if your problem is realistic. So this method of material selection, this is different from divergent thinking. Divergent thinking being you just throwing a dart uh, into the dark and choosing a material, analyzing that, and then throwing another dart and analyzing a whole skew of materials or a whole school of materials, um, trying to pick the best one there. Instead of that messy method, what this does, it converges and narrows your choices down to a set group in which you basically choose the best choice from that group. And it makes this process a lot more efficient, more optimal, and more time saving, convenient, and more likely to uh, keep your function properly alive and healthy. So in this lecture, now we're going to go into the next part, which is Ashby Plots. That's your main tool for determining proper material choice. Ashby Plots. Um, Ashby Plots are very simple. They're just scatter plots of two or more properties. Um, it can't any two properties, honestly, but most likely properties that are relevant to one another of different material classes. So this is an example of an Ashby plot. You have different material classifications in the shaded regions here, like foam, polymers, metals, composites, etc. And then you have the actual groupings of the materials themselves, these actual indicated ovals here. The one thing I want to know, so this is straightforward. This is you basically can pick your material from different magnitudes of properties for Young's modulus versus density on this Ashby plot. The one thing I want to notice, just because there's a category, and just because you could choose a point within a category, if that point doesn't land on any of these groupings or identified spots, there's a good chance that that material might not exist in the market, or might still be under research. So when you go and utilize these plots, you want to go and pick a definitive group within these categories. You don't want to just go pick an empty space here. There's a good chance you won't be able to retrieve that material. Other thing I need to mention, anything that is not within these shaded regions, they just don't exist. So yeah, there's no material that matches these properties, these value properties, and no materials that matches these value properties. So don't bother with those or empty spaces. So how to use Ashby plots. So there's two ways of using it. The first way we're going to talk about is visual. And visually is really easy. If I ask you, if we go to the metallic alloy category and I ask you, hey, which metallic alloy is the lightest, which is the heaviest, stiffest, or least stiff, right? You should be able to indicate which is which just from looking at the graph, just doing a simple graphic analysis, right? So here we are zoomed in on the metallic alloy group. And if I want to choose, if I want to see which one's lightest, well, I just need to choose the one with the lowest density, and that's magnesium alloys. The heaviest and stiffest with the largest Young's modulus and largest density, that would be tungsten alloys, and then the least stiff is lead alloys. All right. So that's how you would visually use Ashby plots. Now, the thing about visualization is that it narrows you down into a focal area of the Ashby plot, but it doesn't give you a definitive way of telling if a material is better than another, or a specific material is better than another, because some groupings are way too close to each other, right? So that's when you would use, in tandem with a visual analysis, you would use a quantitative analysis on an Ashby plot. And what a quantitative analysis allows us to do is we allow to put a definitive number on each material candidate that we so choose. And depending on our situation, that number being higher or lower than another comparable candidate could mean that that material is better, right? So basically, we compare materials by a quantitative number, and that lets us know if it's better in comparison or not. So when we do quantitative analysis of Ashby plots, we usually follow these steps here. The first step is derive the value index. The value index is the quantity we use to pair or compare one material to another, right? And right here, I note that when you derive your value index, you also have to establish your bounds and controls. Bounds being properties or variables or parts of functions that you can't control, like loading. And controls are things that you can't control. For example, the material properties, stiffness and density. So by doing that, you're basically able to identify where in derivation your value index is going to be prevalent in deciding your materials. So that's very important. The next step is screening. You apply your limits. Basically, if you have a minimum density you don't want to go under, then you apply that onto the Ashby plot so you know which region of the Ashby plot you don't want to enter, all right? And we're going to go through an example of that so you'll see, so it becomes more evident rather than just announcing it. And I say right here, in some instances, these limits must be self-imposed. I'll get to that in a bit, all right? So after you apply your limits, you rank the indices. Now, this is where you compare them with one another. This is where you determine which one's better than another. Either higher or lower, whichever one is better suited for your application. Once you pair these two, once you have a list, now you can choose which material matches your needs. Of course, you also need to do a documentation deep dive after that. What that basically means is just because you do these rankings and just because you compare these based on one Ashby plot, you have to look at other desired attributes, like for example, corrosion or thermal expansion or cost that might affect your final decision. All right. So sometimes even the best ranking for a specific plot might not be the best overall material in general. So it's best to illustrate this through an example. So I have a simple beam, simply supported beam example here. And all we're trying to do is we're trying to choose a material, a best fit material that can minimize the deflection at the center of this simply supported beam while keeping mass as low as possible. In addition to that, we also need to keep the density of material lower than water. It needs to be less than water, and it cannot be porous as well. So something like wood that absorbs. So we can't have it be porous. All right. So those are our criterias. Those are our restrictions. Let's go ahead and start the problem. And the first thing we do, we need to start deriving the value index. And the first thing you do when you derive the value index is that you establish your balance and controls. Here I have my balance and controls here. All right, so my balance deflection. The deflection is something I have to solve, and maybe sometimes your customer requires you to not go past a certain deflection magnitude. So that you probably don't have any control of. Loads like this point load here is usually just a given. It's usually what is already attributed into the problem naturally that you're trying to solve and mitigate. So we can't do anything about loads. This is what we have to deal with. And then usually when you deal with beams, you already have a set predetermined length in mind. So we're going to assume here that I can't change the length either, okay? What I do have control over is the cross-sectional dimensions, which is why I mentioned inertia here. That's more for a design purpose. Since we're trying to aim for materials, we also have control over the stiffness modulus and the density, which is going to affect our mass and deflection values, right? So to start off, we're supplied with, or you can look this up easily, the maximum deflection of the beam at the center of the simply supported beam when it's under a centrifugal point load. Derivation is simple. The first thing I do is I substitute the width times height cubed divided by 12 term into the inertia term. So I get this expression right here. Next thing I do, I multiply the top and bottom of the numerator of the deflection equation, and I get a expression for volume at the denominator. And I can just go ahead and move that to the left side of the equal sign and move the deflection term to the denominator. And here I have this expression. So why do we want to use volume? Because volume, it relates to mass. Mass equals volume times density. So I can substitute this equation into this expression right here, and I get this following expression. And then, yeah, when you basically factor out coefficients, etc., you get this finalized equation right here. And the one thing I want to know on this equation is that mass and deflection, you can interchange them across the equal sign, right? And our goal is to minimize both of these so we can have minimal deflection while saving weight. So regardless of where you put these two, these guys are inversely proportional, which basically means there's some quantity in here we can affect that can decrease both of these at the same time, essentially, when it doesn't have to deal directly with either of these two variables. So so we basically think of our controls. What can we control? Well, let's just assume we've decided what our or we've designed what our cross-sectional dimension height is going to be. Now the only thing that we need to control is the material itself, which is this quantity right here. And if we want to minimize the mass or minimize the deflection as much as possible, if I decide to move this quantity into the denominator, it'll become something like this, stiffness divided by density, all right? And in order to minimize mass, we're going to have to maximize this ratio right here. That ratio is what we're going to use as our value index or index value. That's the value that we have to try and optimize in order to get in order to get a proper material to be sub implemented into this solution, right, or sub implemented into this system. So here we go on the Ashby plot. So we already derived the value index. Now the value index, since it's density divided by or stiffness divided by density, is essentially a slope, and it's what we refer to as guidelines on the Ashby plots. All right. Now you might notice there are different guidelines here. I'll mention that in a bit, but these guidelines have different magnitudes throughout the Ashby plot. As you move in this specific plot, as you move to the upper left, the value of these guidelines, the value of these value indexes increase. And what we're aiming for is to maximize the value index to minimize deflection and mass. So what we want to do is we want to move perpendicular to the upper left of this graph in order to get an appropriate material for our problem. Now, second thing you need to do is screening. So you need to apply the limits, and one of the limits was it has to be lighter than water, and water is 1 megagram per cubic meter. All right. So here I applied my attribute limit, and anything to the left is fair game, is material that can be used from this attribute unit. Anything on the right has to be excluded because it fails our requirement of being lighter than or being less dense than water. So that's how you apply your attribute limit. And now you rank the indices of the border here that of our existent choice materials or candidate materials. We have to go ahead and go through each available choice and then rank the indices, or the density divided by the stiffness divided by density, in order to, again, choose a proper material for our application. So we start off with the best choice here, which is balsa. Of course, there's ash and fine coke, but balsa has a higher value, higher index value here, 13.33. The next one with the highest index value is 2.11 for polypropylene, and then there's the rest, right? So from the rankings, you would assume that balsa would be the best. Well, if you've worked with balsa before, it's extremely weak. There's another thing balsa's really bad at. It's porous, and it absorbs a lot of water. So our requirement is that it has to be non-porous. That's where the deep dive documentation comes in. Just because balsa is the best choice on our ranking list doesn't mean it's the best choice overall to fit our problem. And when we do a deep dive analysis and we look at the other attributes, balsa is a porous material, cork is a porous material. So we basically have to eliminate them from our candidate choice. Now, from our rankings, the only thing that exists, or the only thing that are available and appropriate to use for our system, is polypropylene, and then high density polyethylene, and then this final group right here. Of these guys, polypropylene is the best choice, right? So that's how you conduct a quantitative analysis for a specific problem. In this case, we had a simply supported centrifugal beam problem, and determine the best material for that function or system. Now, I mentioned this earlier. There are different value index or guidelines prevalent on this chart. What happens is when you do the derivations for value index, sometimes it becomes repetitive, as in some situations are clearly identical to others. So the value index that you derive is going to be similar as long as it's not unique. So what engineers have already done is they've created a table. They've created a quick lookup table. And if your problem matches these specific situations, then you can go ahead and refer to these value indexes and then use them for your Ashby plot, on your Ashby plot, so you can have an appropriate guideline and understand where you need to go, either maximize or minimize your value index, where you need to go to choose the apt material, right? So since we're working with minimizing the weight while having a centrifugal load, we had this application in mind, or we have this value index in mind. this square root of the stiffening matrix divided by density, that's if you have some kind of minimum weight design of a beam or shaft or column that you want to optimize. That's when you would use this value index. Okay, so there is a lookup table for that, but I would suggest you do the derivation first and then pair it with the lookup table to see if your situations match with already pre-existing repetitive derivations or recorded derivations. So I have other examples here. This is a slender column buckling problem and how to determine the derived value index there. I have another more advanced problem where we talked about curved beam deflections and how you derive the value index using energy theory. And that's for you to use. That's for you to look through the notes after this lecture if you want to use this as reference. So I provided that for you. But the main thing I want to note from the end of the curved beam deflection slide is the constriction of one of our boundaries here of our Young's modulus. What I mean by that is one of our bounds is deflection, and let's say in a customer requirement, you're only allowed a certain amount of deflection, and let's say you already have a cross section in mind, right? If you already know how much deflection you can't go past, and you already have a predetermined geometry, then what you can simply do is you can move this known bound term to the denominator, and you can move one of the control terms, which is here, it would be the Young's modulus, to the other side of the equal sign. And what that essentially does is it creates an attribute limit or a self-imposed attribute limit. So we basically know what the minimum Young's modulus we need to satisfy this criteria based on the customer requirements. And that's what I meant by, in some instances, these limits are self-imposed. If you know what your customer requirements are, you can utilize your balance and controls to generate a limit and help narrow your choice even further on your Ashby plot. So this is an example of us from that curve beam deflection problem. It's an example of us applying a minimum Young's modulus attribute onto the graph. All right, so just keep that in mind. That is a helpful shortcut to help with material selection and further narrow your choices. Right. So now the mention of other Ashby plots. So I've only shown you the Young's modulus versus density Ashby plots. In reality, there is many different Ashby plots for different comparisons of like materials or materials that are relevant to one another, or properties that are relevant to one another. And when you do your deep dive analysis, it's encouraged that you look through multiple different Ashby plots of different materials of relevant properties, and usually just cross-check them, cross-compare them to one another to see which material overall or which choice overall best matches your system or function. A simple example is if I had this kind of Ashby block here where I had strength versus density, and I've already done the value index derivations. I have no attribute limits. I have no other requirements, etc. On this plot right here, I want to maximize my value index. Turns out Diamond has the best value index, right? So you would think that we should use Diamond. Well, there's one other aspect, or there's one other attribute that we have to pay attention to for any project, and that's the life of the project, which is budget. So Diamond is really expensive. It would be somewhere around here on the weight per cubic volume axis here, and weight in terms of grams, that can be converted into a monetary value easily. But diamonds is just really expensive, right? So if you decide that your structure is going to be all diamonds, and you had a 1-year project or a project with a 1-year timeline and enough in budget for it, if you use all diamonds, you're going to basically blow out that budget in less than a week, right? So even though diamonds are the best choice here in terms of strength to weight ratio, they are not valuable, or they are not uh, uh, they're not appropriate for this certain kind of application because they waste too much money. So that's what I mean by doing a deep dive and comparing other attributes with other Ashby plots. Looking at different perspectives from different Ashby plots will allow you to choose a proper material that won't damage your product and will have the and will be efficient enough to do your systems functionality essentially. So uh, now that I've just talked about the I've talked about the examples of how to use Ashby plots. Let's go over how you can apply this to your guys' projects. All right. So um, and I'm just going to start the process here. I'm not going to go all the way through. The final decision of materials is on your guys' hands. I'm just going to basically give you an idea of how you would approach these kind of problems with something like a microbioreactor. So uh, this is the project statement, or the problem statement I was given by Dr. Trom for one of the one of your functions or one of your systems that have to preserve your operation within temperatures of 4 degrees to 70 degrees Celsius. So that's a limited requirement that we have to deal with. And what I want to try to prevent, being one of our customer requirements, is thermal distortion. So something like plastic basically distorts somewhere around 74 degrees Celsius Fahrenheit, or 74 degrees Celsius or higher. I want to try and make sure that when I do my operations, my system does not distort. And at the same time, uh, for an additional customer requirement, it's preferred that we would try to keep this system as insulated as possible, so it's not too hot to touch. So I have these two requirements here. I'm mostly going to value thermal distortion here, but yeah, these are my two. Primary limits that I have to work with, and try to select the material that's most apt for this module or for the system. Um, the other thing I'm given is this 15 minutes of terror, which apparently, so according to Dr. Trump, you guys only have 15 minutes after your operations or functions are finished to return whatever operation, whatever's inside that vessel that you're conducting that operation, to its initial conditions. All right. So uh, the problem of diffusivity, you might want to try to cross-check it with another type of Ashby plot. This is where you go into deep dive documentation and see if your material selection promotes diffusivity, or basically going from steady state to transient. We'll go over that in a bit. But yeah, that is just another attribute requirement that you have to keep in mind when you're selecting your material here. So let's go through the example here. For my function, or for my system, I decided that the microbioreactor is going to work inside a cylindrical vessel for whatever reason, just for my design. And I need to analyze, and I need to choose an appropriate material that will minimize distortion as much as possible, and not have not have too much conduction, have enough insulation so it's not too hot to touch. And when I do this analysis, now this analysis is rigorous if you do this in a 2D or 3D case. So I'm going to make assumptions to make this analysis easier, because we're engineers. We can make these problems a lot easier for us if we use appropriate assumptions. And basically you have the advantage of controlling how difficult the problem is, or how much you need to address in the problem. After you make these assumptions, of course, you have to go to your boss and then ask if these assumptions are right or not. And he'll probably tell you, no, you can't use this assumption, or yes, you could use that assumption. And you're basically going to have to work with what you got. But for now, we use assumptions to simplify the problem so we can make it solvable. So I'm looking for a value index. So my assumptions to help me with that is that I'm going to assume that it's an isotropic material, and we're working with elasticity, and we're working with small strain deformations. The other thing I'm going to assume is that the expansion is primarily going to be in the radial direction. So anything in the circumferential, which is tangential or due to shear strain, any deformation due to those factors are going to be neglected. I'm going to assume the heat transfer is primarily radial. So circumferential, out of plane heat transfer to those other two directions are going to be negligible. And then conduction through the wall is going to be considered linear. And that's going to simplify one of my cases, as you see later on. Some might argue that these two examples right here, making the other two directions negligible, it's not that great of an assumption, and I would agree if I'm doing a little more rigorous calculation. But for the sake of simplicity and for the sake of being able to solve this with common physical understanding or comprehension of what I'm doing, I make these assumptions so that it's easier to go through the derivation, right? Now, before I solve the value index, remember when I said you need to solve the value index first before you work on the screening and limiting attribute? When I did this problem, I sort of did this unconsciously because this is usually what I do. When I'm given a set of requirements, a set of limits immediately that don't necessarily apply to what I'm trying to solve through my value index, when I'm giving a set of limits such as surface temperature uh, boundaries, I usually go look for a plot and try to apply my boundaries first for surface temperature and also strength too. You probably have it's a modular, it's a system inside. It's a mechanical system inside your part, so you probably have a minimum strength requirement. Say my minimum strength is 7 megapascals, but since I'm already given a limitation on how much surface or what my minimum surface temperature is, I can just go ahead and take advantage of that and apply those attribute limits to this Ashby plot right here, which is strength versus maximum surface temperature, and then choose or pick a set of available materials within the valid regions. And those are materials, as I go on through the analysis, those are materials I'm going to be paying attention to, right? And by doing this, this simplifies the process and makes it more narrow, makes it more streamlined, and makes it easier to bookkeep what materials valid and what materials is not. So in this case, even though all these metals are valid, lead alloys are not. They are below the required surface temperature. So I can immediately eliminate a property that immediately doesn't fit my needs. So an immediate elimination makes this process a lot easier. So that's a case where you can do screening first to make things a lot more streamlined for you. So I just want to note that this plot right here has no value index. And usually you're going to get Ashby, and when you get Ashby plots that have no value index, it pretty much means that these two properties aren't physically related to one another. So maximum surface temperature and strength don't have a derived equation or don't have a derivation that relates the two physical quantities into a guideline, right? So some Ashby plots, if they're relevant, they're going to be relevant because you can apply limitations and you can establish where your boundaries are going to be and narrow your choices more. Other than that, they really have, if they have no relationships, they're probably not going to be useful. Okay, so I'm going to speed things up a little bit here. When I do the derivation for the value index, I'm going to use the assumptions I made along with basic mechanics, material principles, and thermal analysis. So I said earlier that the main distortion, main direction of displacement due to distortion is going to be in the radial direction. So I'm going to assume every other direction is going to be negligible, approximately 0. I'm using polar coordinates since I'm working with a cylindrical vessel. And the small strain Lagrangian assumption for radial displacement or radial strain is the partial derivative of the displacement in the radial direction with respect to the radius or position in the radius. But since we're also working with thermal expansion, this is primarily a thermal expansion problem, and we're working with assumed isotropic material in the elastic region, we assume, or we know that the equation for thermal expansion that relates to strain is the thermal coefficient of expansion multiplied by the change in temperature from the inner and outer radius of the vessel I'm working with. So I can rearrange these equations and I can make it all equal to the change in temperature. And I get this expression, and we're going to use that in a bit. Now we work on the heat transfer side of things, where we have the heat flux equal to negative of the thermal conduction coefficient times the temperature gradient. Now I said that the temperature or the heat transfer primarily happens through the radial direction. So and I also said that it happens linearly through the radial direction. So what that essentially means is that I can approximate the gradient, the temperature gradient, as the change in temperature across the wall thickness divided by the change in radius. And what that approximately equals to, the change in radius, is basically the thickness of the walls. All right. So I can rearrange this expression to equal change in temperature, and I get the following expression right here, where I take this expression, I make them equal to one another essentially. And so now I need to solve for, or I need to create an expression for displacement in the radial direction. So I'm going to go ahead and do some quick calculus, and a little bit of algebra. And I'll arrive to this equation right here. Now, there's a constant in this equation. No matter what your boundary condition is, so you have to apply your boundary condition to solve for this constant, but no matter what your boundary condition is, this constant does not affect, it's a constant, it does not affect the overall quality or quantity of the control valve. It does not supersede the authority of the control index here that determines, or that we're trying to use to minimize or maximize our or optimize our current system. So whatever value you choose here, this index is always going to factor out. So you don't have to worry about it. You can also just do the analysis yourself to prove it to yourself, right? So yeah, we have this equation here. We have displacement, which are representative of distortion in the radial direction, equal to all of this. And there's this factor right here. This factor, expansion divided by conduction, or thermal conduction. This is known as our thermal distortion ratio. This is the quantity we want to try and minimize in order to minimize distortion based off this equation right here. So we're going to make that our value index. We're going to make it, and of course I throw this in a denominator. We're going to make this so that the thermal coefficient, our thermal conduction coefficient divided by the expansion is our value index, and we need to maximize that in order to minimize heat distortion. So simple enough, but the thing to note here is that if I decide, okay, instead of focusing on distortion, maybe like the mass and deflection example, for the centrifugal beam example, I can switch these two and I'll have the same case where I have to maximize the value index. That's not the case here. What happens is, if you decide to move the heat flux to the other side of the equation and then our equivalent distortion displacement into the function, what happens is you now have the inverse. You now have to minimize your value index in order to minimize your or maximize your insulation while minimizing expansion as much as possible. So that's an example where the properties of expansion and conduction become competing factors. If you increase one, you decrease the other. So basically, now we're limited to a choice, and you can see this on the Ashby plot here. If we try to decrease expansion, we have more conduction, and vice versa. So now we're limited to a competition where we have to decide which one's more valuable. Do we want to minimize expansion, or do we want to minimize conductivity? For me, for this problem, I want to minimize distortion. All right, so I want to maximize my value index, so I have the minimal amount of expansion while having an acceptable amount of conduction that I have to work with. So pay attention to this Ashby plot here. The conductivity term is on the horizontal axis, while the expansion on the vertical axis. That basically means your value index increases. This value index increases as you go to the bottom right. So it's just a word of note to pay attention to your graphs when you're working with them. And to minimize the value conduction, you'll go to the upper left. But we value distortion right now. So of the candidate materials I chose earlier, I've already ranked their index values, right? So the choice of your index value limit is up to you, all right? You can go through this equation. You can go through, if you know the value for distortion, displacement, if you know the value for heat flux, you can probably already set an attribute limit. You can already set a existing attribute limit for your value index. If not, you're going to have to do some other somewhat tedious method of analyzing and then deciding what your value limit is going to be. And here I have 3 different examples of 3 different value limits I choose, and which materials become acceptable. Acceptable based on where they are relative to where I place the limitation line. So if I have a value limit here, that basically means, and I want to go to the bottom right, every one of my available material choices right now is onto the bottom right side of the value limit. They're fair game. As I increase the value limit, polypropylene becomes inappropriate for this application. So we have to eliminate that from our choices. As I increase the value limit even more, if I decide I want an even higher ratio, then I eliminate silicon glass and carbon fiber reinforced polymers, and now I'm left with aluminum steel. All right. So your choice of value limit also determines how you narrow your choices for a specific Ashby plot too. So again, that is pretty much your choice to make. And if you understand, if you know what your limitations are, you should apply them, and then that will help you that will help you down select your choices even further. Now remember, even though lead alloys are in the bottom right side of this graph here, does not mean that they're appropriate for this application. Again, they don't meet our service temperature requirement, which is why I did the attribute limit narrowing process earlier with a different graph. So that's an example of using a screening process on a different graph and deep diving meshing it into the current problem and taking advantage of that to make the process even simpler and more streamlined. And I'm not going to go through these other properties in detail, but now that you have a decisive ranking list for what's most appropriate for your thermal distortion limits, you probably want to focus on the other requirement now, which is the 15 minutes of terror. And you want to probably have a high diffusivity if your vessel is part of your restoration process, right? So you would have to do another deep dive with a different type of Ashby plot. You will have to rank your value indexes here. And of course, don't forget about cost too. Cost is also really important. So you'll have different ranking lists for different Ashby plots. And what you do at the end is that you basically do a down selection process. You cross-examine each ranking list, cross-compare them, and then ultimately decide a material with your team. And you're going to have to argue with this in your report, and just in future projects, you're going to have to argue to your customer and to your employer, whoever's hiring you, why you chose your specific material based off all these different attributes that align with our goal for the system or our idea of how we want the system to function. So basically, in summary, down selection is a case-by-case basis. So different functions, different systems have different material requirements. You have to do if you have to do a quantitative analysis, you have to derive a index value, or you can look it up. And whole use of the Ashby plot as a tool for material selection. It is not a complete streamlined process. By that I mean it's not going to give you the definitive final material that you use for your product. What essentially it does, it narrows the selection into a focal group, and you have to decide, along with your team and your customer, which material best suits your need. And there can be a lot of uncertainties that you have to consider, but you have to keep that in mind in order to determine a more efficient and productive, or efficient and optimized way of making your system work without potentially damaging or uh, yeah, uh, making anything else in the system worse. So when you finalize your ranking list for using the Ashby plots, you basically cross compare them, and then you do the down selection process, and you ultimately, with your team, choose which material is appropriate for your applications. Okay. So that pretty much concludes the material selection slides and presentation. And if you have any questions, just feel free to ask me. Send me an email.
Okay. Thanks, Brandon. Well, we're still recording. If anyone wants to ask a question that's like relevant and specific to the slides in the presentation, now is a good time. So we'll entertain any questions if people have them.
See if I can open up chat. Oh, there we go.
Okay, looks like no questions. Okay, so let me stop recording then. If there are no questions.